Hi, everyone. Can you all hear me okay? Is the levels right? Great. My name is Anil, and I'm a researcher at the University of Cambridge, where we do a whole bunch of fun kind of open source hacking and things like we worked in Xen when it was first a research project, and more recently been working on a lot of experimental microkernels and ways of doing data processing. So the work here I'm going to talk about is with my very fun colleagues from both Nottingham and from Cambridge, and you can see their names up there. And it began as a bunch of experiments in building microkernels, as I said. And it turned into something a bit odd. It turns out these days that IPC, which was normally not a really big problem in Unix, it was something that, say, a Xen geek or an L4 geek would worry about. And it turns out that IPC performance, that is inter-process communication between processes, is turning into a really, really important factor in Unix. So how many, just to give me an idea, how many people here use virtualization in some shape or form? Sweet. How many of you have a multi-core machine, say with more than two cores? Actually, yeah, pretty much all of you right now. And so there's actually these reasons why IPC is moving beyond a niche problem. It's because our privilege layers, as we walk up through the software stack, are increasing. So whereas previously you'd be running directly on the bare metal, these days it's pretty common to have some kind of a layer between you and the hardware. And this is in the form of a low-level hypervisor like Xen or VMware, hosted hypervisors like KVM or VirtualBox, which are in many ways much easier to use. And even increasingly, high-level language runtimes also impose privilege boundaries as a result of the desire for more security. At the same time, this vertical increase in layers is also being followed by this whole trend towards NUMA architectures. So if you're of a certain age and you worked on say SGIs in the 90s, you'll remember NUMA was very relevant and a big feature in the big iron operating systems of that time. These days we're heading in exactly the same direction. So in just the last 5 years, we've gone from hyper-threading as a quick hack by Intel to let us exploit a bit of parallelism, and now it's very common to have NUMA machines and multi-core machines. So I'll actually talk about some of the experiments we did around this, just to see how bad the impact is. So just how much do we have to worry about this? So I thought I'd give you a quick sneak preview of some of the performance results. So in many cases, we're observing performance improvements if you suddenly become NUMA and locality aware of, say, 6 times an AMD. And this is from going from a TCP connection to an optimized shared memory transport. And similarly, on Intel, on the newer i7s, it's often even worse. So in this case, going from a TCP no delay algorithm to a shared memory transport that I'll describe during my talk resulted in just hundreds of gigabits of throughput versus tens of gigabits. Now, again, why should you worry? If you're, say, using the cloud, then increasingly memory-to-memory communication is the way that you communicate with virtual machines. So if you're on Amazon EC2 and you have a web server and a database server, then you will, of course, be sending a lot of data between them, and this will eventually take the form of IPC, just memory-to-memory communication between hosts. And actually hitting a NIC is relatively rare in these kind of big iron deployments. So for my talk, I'm just going to break it into 3 bits. First of all, why it matters, and I'm just going to show you some fun benchmarks that we've been running. And then I'll talk about what some of the fixes we're trying are, but of course, that's just one of the possible attempts. And also, since this is FOSDEM, the reason I'm here really is to try to rally some help for an experiment in data gathering that we're trying. Because of, obviously, we're just a very small research group, so we need some help from you guys. So let's try an experiment. So we have a 48-core box. We bought it for about, I don't know, £7,000 or something. It's got 48 cores. It's quite a lot of cores. It's got 64 gigabytes of RAM. And it's running an AMD Magna-Core processor, running Linux 3.1 on x86-64, and an unmodified Xen also in 64-bit mode. And all of the tests I'm going to describe are running in RAM. So very straightforward. And so what are the experiments we're running? So we thought, well, in order to figure out, are all these cores really made equal? Why don't we just run some latency tests between all of these cores? So by running these latency tests, it's very straightforward. You just run the full combination between all CPUs, but only one at a time. So you might measure the performance between core 1 and core 6. You pin the processes, so they're only running on core 1 and core 6. There's pretty much nothing else running in the machine. Everything that can be killed is being killed. And we then plot the grid of combinations. So we plot x and y of core 1 to core 6, and et cetera, et cetera. So it's a pretty straightforward way of just exploring your system. And so in terms of what are we measuring the latency of, well, there's a whole bunch of mechanisms I'll describe. So things like TCP, UDP, some shared memory transports between them, and also things like pipes. So why don't we take a look at the first result? So this, as I described, is our 48-core machine. And the x-axis marks the source core, and the y-ID marks the target core that you're going to. And the grid, each of these little pixels represents a single test. So there were a lot of tests run for this particular result. So does this kind of make sense to anyone? You can start to see patterns in this, right? So what are some of the patterns that we can see in this? What does it tell us? So first of all, blue is the lowest latency. So this is actually measuring latency on the bit for each individual message. So you can see here that if you're on exactly the same core, then you're actually not communicating across cores. So we've actually got pretty good latency for TCP. It's the lowest, most efficient way to talk to someone is obviously to talk to yourself. Then what are all these other crosshatch patterns? Why are they in such a distinct order? Well, to answer this question, you need to start looking at the hardware architecture that the machine is running. So this seemingly flat layout of cores is actually interconnected by something called hypertransport. And it's actually a very hierarchical mechanism, right? It's all laid out. AMD does not make a 48-core CPU. They make 6-core CPUs, and they pack them into what's called a multiprocessor module. Then those 6 cores are packed into a socket, which is actually about 12 cores in size. And then you have these inter-socket transports that actually decide how to lay out connections between each of these things. They're laid out in kind of a grid pattern, so you can see that this NPM is connected directly to this one, and it goes through a slightly longer interconnect to go to other places. And this is just one machine, right? So this is required digging into the usual reading AnandTech and some of the AMD hardware manuals, just trying to figure out exactly what it looks like under the hood. So given this actually makes sense, right? So we can see the fact that if you're either going to your near socket or if you're going to a further socket, there's a very distinct gradation between the various communication mechanisms. So great, this is totally obvious. So what happens when we start adding some of these software layers that I described? So let's take the exact same test and let's virtualize it. So this just means we boot Xen, and the domain 0, which is the controlling domain, is now running 48 vCPUs. And this should be no different, right? Because you're just you're not really running any further virtual machines. So what happens? Well, things do start getting a bit more random. So can anyone here explain why this might happen? And I'll just put both of these graphs up here just so you can see what's going on. This is the same. This is just a 48 vCPU Xen, and this is running on native. Any ideas? Go for it. Right. Right, precisely. So just to repeat the answer, he says that, did we pin the vCPUs? And so the answer is no, we just set up a domain. Now, the expectation is that if you have just one domain running, your scheduler is probably not rebalancing the CPUs. But what's actually happening is that even though you just have one domain on the box, Xen is in fact remapping the CPUs dynamically. So this is effectively just noise. We have no idea what the underlying topology of the hardware is at this point. And the absolute latencies, interestingly, are double. But it's not really the absolute latencies we're worried about. It is, as you say, just what is the effect of rescheduling on this domain. So this is, of course, an advantage. You want Xen to figure out and rebalance your CPUs. But sometimes you don't. Sometimes you just want to have control over what's going on. And especially when you have just a single domain, it just adds another layer of scheduling and multiplexing onto the hood. So what happens when we try to pin the domains? So you can take a hypervisor. You can run, in the case of Xen, you can run XL CPU pin. And so we pinned 0 to 0, 1 to 1, 2 to 2. And you have a pCPU ID and a vCPU ID. So in this situation, now you can see that we can actually start to see a topology underneath Xen. But it's not the same as the one that we had last time. So this is the pinned version. This is the unpinned. So it's clearly more predictable. But if you compare it to the native version, it's just a little bit different, right? And so again, the reason for this is that it turns out that when you the Xen enumeration mechanism for CPU numbers is different from the native one. So it's consistent. There's always a model of what that is, but it's just different from the Linux enumeration because of various details of ACPI and so on. And so the other problem with this is that it requires root access to your cloud, right, your cluster. So the only people with access to this sort of level of the system administration hierarchy are people who control the clusters. If you are just running a high-performance job on Amazon, you wouldn't be able to do this pinning. So again, the problem with these layers is that you add more social layers as well, and people who can and cannot control this stuff with other people. So the problem is that we can almost predict it, but you really have to run the experiment to figure out exactly what it's going to look like. And of course, this isn't just on one machine, right? So why don't we try something else? Why don't we, what are the effects of NUMA? So instead of using TCP, just pick a simpler transport mechanism. And in this case, we picked UNIX domain sockets, which should be really just memory-to-memory copies with very little CPU usage. And I'll explain some of these differences later on. Now, you can see here that this is less clear than TCP, but there's still an interesting effect where if you're on the same local socket, you can see it's much lower latency, and it's generally just more latent outside of your local socket. But it's still very clear. There's this pattern of staying within your socket is a good idea. So what happens when we run this one under Xen? Well, you get an entirely different graph, right? And it's not random. There's clearly this trend, and tracking this one down took a little while. So who reckons they know the answer to this one? So far, I'm buying you a beer because you guessed the pinning. If someone else can guess this, you get the free beer. Anyone? Any ideas why? Oh, all right, Richard, you get the second beer. Although you don't count, you work for Red Hat. That doesn't work. So, so what's actually happening here is that whenever you allocate memory, memory is also in a hierarchy. It's attached to what's called a NUMA domain. And so the NUMA domain basically decides when you run malloc, it decides where you allocate the memory from. And usually that's based on what CPU you're associated with, what core you're running on. So in this case, we should be allocating it on our local socket. And in fact, in the case of native, it is. But the problem is that Xen actually, and in fact, many hypervisors, although one of the reasons for coming here is try to figure out what other hypervisors do, apart from digging through lots of source code, is that they don't actually expose the NUMA layout to the guest. So it actually just tells it to always allocate from memory in domain 0. So in fact, whenever we're allocating these buffers, the further we get from domain 0, the more latent it gets. So again, it's kind of not obvious, but it's starting to see just how much of a difference it makes. All we're doing is just, in our hardware, just picking a different part of the topology to work from. So we've done a lot of digging, right? And we've gone through, and this is just a small subset of the experiments. And I'll show you a website where we have lots and lots more experiments. And there's something we just cannot explain. So I will definitely buy someone a beer if you can explain. Only in the case of domain sockets and not in the case of anything else. If you're on the same core, domain sockets are more latent than if you're running on native. But in the case of TCP, in the case of other transports, this is not the case. It only happens in some versions of Xen. So some things are ongoing research while we still try to dig what's going on. But it's very, very, very clear that there's a lot of layers of software in play here, right? And things are only getting worse. There's just more and more stuff happening. So the easiest way is, obviously, if you're trying to do a bit of science, is trying to establish the absolute lowest bound. What is the simplest possible mechanism by which we can discover a property of our computer? And so this is actually something called inter-process interrupts. So whenever we have these 48 cores, they can send an interrupt to the other core. And this interrupt will wake up the other core and tell it that something is happening. And it then goes off and looks at its various I/O channels to figure out what's going on. So oh, awesome. So the hypothesis here is that the traffic is going through domain 0 and it's being looked at twice. Now, it's not quite true because memory is directly mapped to the domain. So it's coming from the NUMA node that DOM0 is in. But also, unfortunately, the memory is actually allocated for all of the socket backends from the same memory node. So TCP should be the same as Unix domain sockets in this case. But let's talk about this afterwards, because I didn't ask the audience for that, because we've spent hours talking about this one, right, and trying to track it down. So, but it's definitely, there's something in there, but we're not quite sure what, and we're working our way through it. But getting back to IPIs, what we did was we modified Xen, so there are no domains running at all. So at start of day, the hypervisor comes up and is just configuring its CPUs, and then it starts playing a little game where it ping-pongs between CPUs. And this graph just shows us in nanoseconds, so it is really very low level, and you can very clearly see the microarchitecture of the underlying domain. So having this kind of self-test, just a few layers of your software up, is actually quite useful just for getting hard data into what's going on. Now, Citrix very kindly lent us this beast. It's called HydroMonster, right? And HydroMonster is a 160-core machine Westmere EX-based system, very expensive, very nice, and also completely different. And so if you dig through the Intel architecture manuals, it turns out that the Westmere has a bidirectional ring between CPUs, and this actually reflects in the fact that when you're talking to a different socket on one of these machines, then the individual core you're addressing within the socket makes a big difference as to what's going on. So it doesn't matter if something's near or far, although that matters too. It also matters who you talk to on the other side, because you're going over this ring structure. So the point I'm trying to make is that it's just really hard to know what's going on, right? These are just two machines are described, 2 bits of software, and there's lots and lots and lots of layers. So what on earth can we do to try to fix this problem? We know that it's probably quite varied. We know that we're going to have more layers of virtualization. If we deploy the Internet of Things, for example, the Internet of Threads, my apologies, from the last talk, we're clearly going to have a lot of variance in this kind of stuff, and we'd like to maintain, gigabit and low latency performance, right? So obviously being researchers, we thought, let's set a challenge and let's just go hack up a benchmark over the weekend. It's just a few grids. How hard could it be? And it turns out that, yeah, the devil's in the detail when you look at Unix I/O. So the first part of designing one of these benchmark suites is pretty obvious. You have to take a variety of transports, just different ones, and hopefully some of the common ones that we use every day in our software, and some slightly less common ones that I'll talk about shortly. So the four ones are pipes, domain sockets, TCP, and I'll talk about shared memory. So what I'm going to do now is just briefly describe each of these things and hopefully give you an idea of what the costs and the drawbacks are between each of these transport mechanisms. So firstly, how familiar, okay, who here knows the difference between a pipe and a domain socket? Put your hand up. Right, so I think we're talking about 20% of the audience. So in a straw poll of the University of Cambridge Computer Laboratory, I think maybe 2 people knew the difference and only 1 was sure. And he was the guy, Robert Watson, who wrote the FreeBSD code for doing this. So it really is non-obvious between all of these very, very old-school POSIX things exactly how they work under the hood. And it turns out Linux and FreeBSD are actually completely different. Anyway, just because of the nature. So the fundamental decisions that we make with transport mechanisms in Unix are actually quite straightforward. We have a privilege boundary between user space and the kernel, and doing a system call is normally quite expensive. Doing a system call when you're virtualized is really expensive, unless you're in hardware virtualization, when it's less expensive. So it's just a bit different, right? But this varies quite a lot. And also, you're in a different address space when you're in user space, and so moving data between these two can be quite expensive. But in the kernel, it's actually pretty cheap, right? You just transfer the ownership of this memory to another process structure. So with this in mind, how does a pipe work? So when you call the pipe system call in Unix, what's happening is that you have, say, 2 applications, and they want to communicate. So this application is in user space. It writes something into its buffer. Then it calls a familiar write system call, which copies it into the kernel. So in the kernel, this is then transferred onto the receive queue of the other target process. So there's no copying going on here. It's just a bit of housekeeping by the kernel. Then at this point, the kernel, you call the read system call in Unix as normal, and it's copied back into the buffer. So it's a pretty straightforward kind of data flow here, right, that we can understand. Now, of course, some of these transitions have variable performance. So if you're going from user space to kernel, on Xen in PV 64-bit mode, it's very, very expensive because of various technical restrictions in the way you can power virtualize. So we're not quite sure what the costs of these are, but we know the overall flow of the system, which is good. So the difference between pipes and domain sockets is that they actually use the same data flow under the hood, but sockets just have more semantic abstractions. So with sockets, they're guaranteed to be bidirectional, whereas pipes, according to POSIX anyway, are single directional. And the socket semantics that you're familiar with for TCP all exist. So you have a stream mode, you have a datagram mode, you have credentials for determining the next peer. But in terms of just raw performance, it's just a bit more CPU and a bit more memory, but it shouldn't really make that much of a difference. Then finally, TCP is just obviously the juggernaut of data transport, right? So you have the same kind of model as a pipe when you write into a buffer, but then there's a whole packetization process. So TCP has to deal with sequence numbering, reassembly, and the transmission of this packetized stream to either a NIC or another host. So it's just more complicated, and there's more housekeeping. And even when you go to localhost, so if you're just saying TCP to 127.0.0.1, the kernel is still forced to do all this work, because you might introduce a firewall in there, it might have to go through the IP layer. It really cannot just fake out this illusion of TCP. It has to actually do a lot of the work. There's a very few bits in there. So with so far, these are all things that anyone who's programmed a network application would have used. So let's go to shared memory, right? Because ideally, we would never go into the kernel, and you'd always stay in user space. Because this is kind of the obvious thing to do, right? Why do we need this kernel? It's expensive, it gets in the way. I just want to transfer data from A to B. I don't need this thing. So how many people here have designed a shared memory transport? Oh, okay. I need to talk to all of you about it before I leave, right? So this is the bit that took more than a weekend. So first thing is that you have the shared buffer. And this shared buffer needs to have some mechanism of encoding all the various payloads. So previously, whenever you're writing these payloads into the kernel and out, you're writing in the form of individual payloads, right? Read and write. In this world, we have to have a data structure where you have a consumer pointer, which says you have something to read, and a producer pointer. And you have to have the variable length payloads encoded. You have to tell it for synchronization purposes, whether or not this is a valid payload or not. And then, of course, you have to have the list as a bit of a ring. This is a very, very common structure that normally has a subtly different layout between, so for example, Xen uses this to talk between VMs. We use this in user space to talk between applications. But although POSIX in particular defines a mechanism to create shared memory, it doesn't tell you how to communicate using shared memory. There's no standard POSIX sockets version of shared memory for various reasons. And so the question really becomes, how do we synchronize between these two processes? Because whenever I write something, I need to wake the other side up. And that really is where a lot of the variance comes in when you're designing shared memory protocols. It's not really designing this structure, it's figuring out how to wake the other side up using the least intrusive mechanism possible. So if you work in an investment bank and you're doing high-frequency trading, you only care about latency, and that's all you care about, right? You make $100 million if you're 10 nanoseconds faster, whatever the number is these days. What you do is that you would spin. So in user space, both applications would just constantly sit in a loop, testing for a flag, testing a bit of memory, and trying to find out whether or not they should do something with the shared buffer because the other side has written something. And this is normally pretty good, right? Because you're fully utilizing your system, so you're 100% CPU, you're spinning away, and then unfortunately, your IT department decides to virtualize your careful setup, and at this point, you realize that you don't actually own the CPU anymore. So this is the perfect mechanism if you don't care about energy, and you don't care about the fact that you're virtualized and some other domain is now taking all your CPU because the credit scheduler in Xen has decided you're abusing the system. So we can't spin, right? Spinning is kind of what you do when you control everything and you're sure of your environment. So the next mechanism is also, do we trust the other side? So if you go back here, you notice that we're actually writing into a buffer and reading from a buffer. And then because you're just grabbing a shared buffer, what if this application, either by mistake or maliciously, decides to write something in? So at this point, you also need to worry about that. So we also need to worry about things like trust. In the socket API, you never trust the other side. You always get a copy. If you're doing zero copy, you got to kind of figure out, do I copy this into a private buffer or not? How much does it matter if this changes while I'm executing? That's just a decision you make as a programmer. So there's other mechanisms. Linux has something called mutexes, which are fast user space mutexes, and they're pretty cool. What they let you do is that you can mostly stay in user space, because most of the time you don't block. And it's only when you need to synchronize, for example, signal the fact that you want to block and take a lock, that you drop into the kernel, and then you drop back into user space. So most of the time, it's like you're spinning, right? Because if I can write and there's space, I'll just write. I don't need to talk to anyone. And only if I need to wait for something do you call those. The problem with those is that they're not portable. And again, this is an example of where by leaving POSIX behind, you get a lot of cool new interfaces, but these are evolving all the time. And so FreeBSD has an equivalent that's almost but not quite the same. and there's interesting differences between them. Only interesting if you're working in this stuff. Not interesting if you're trying to just do your job and design a shared memory protocol. And so there's a lot of these mechanisms. So some of the observations from doing this work is that the POSIX API is obviously very well understood, but the internals are not necessarily so well understood, the performance implications. And also it bakes in a lot of assumptions about trust and so on. You need at least one data copy. So if you want to build zero data copying, you can't do that in POSIX easily. You need to drop to shared memory of some kind. And also, establishing shared memories, there is no standard for doing that. So we really would like to start thinking about new mechanisms for transport. To give you an idea of throughput, now I'm not going to go through all these graphs, right? But what I have done is if you go to, I'll show you a URL later on. Sorry, it's up there. I missed that. This actually has a number of graphs that we auto-generate from a whole bunch of data sources. And you can see that if you're on the same core, and these are all of the different mechanisms that I talked about, plus some additional ones, the takeaway from this is that performance just makes a big difference. This is the throughput, right? The actual performance throughput. And you can see that we're still in the gigabits, but the poor white one at the bottom is TCP. So this is the one that we often use to connect to your MySQL or whatever. And all of the other ones are just variations on safe or unsafe, shared memory, and on-core and off-core. And it just really is quite hard to predict what's going on, right? But it is clear that if you use TCP, you're missing out. Things are just going really, really slowly for whatever reason. And this could be because of the flow control mechanisms, TCP not dealing with fast mechanisms, or it could just be the fact that shared memory and all of the privilege boundaries are just better. So it's clear that I would rather be up there in the 25,000. In fact, I'll show you afterwards, is that on the Intels you can get up to 100 gigabits that you just cannot even hope to with TCP. So hopefully I've convinced you that it's complicated. And the question is just how complicated is it, right? I mean, I've shown you a few graphs. There's some stuff. It's all a bit variant. So when we actually built some of these benchmarks, it turns out that there's a lot of decisions you make when you want to do I/O. So you start off with some of the ones I described, like the instruction set architecture and the fact that it's Intel-based. Are we virtualized? Which hypervisor? They're all different. They're all good in their own ways, but just different. How do you synchronize? Are you running FreeBSD or Linux? And then more generally at the high level, how do you want to do flow control and congestion? Do you care if you block for a while or not? Or do you just need constant bitrate? Do you trust the other side? And SSL, if anyone has programmed OpenSSL, can be challenging to get right. And there's lots of cool new mechanisms for doing a much more CPU-friendly encryption, like TCP-crypt from Stanford and UCL. And at the higher level, are you using Java, are you using Python, are you using OCaml or Haskell? All of these bindings make a big difference. And so each of these might be death by 10% or 100%. But when you add them all up, if you don't get them all right to align with your environment, you're losing out on gigabits of performance. So we've been hacking on an open source suite, and just to systematically measure this stuff, kind of a self-test in this world. So it's called IPC Bench. It's open source. It's up there in GitHub, and it's very much a work in progress, right? We've been hacking this furiously, trying to do our kind of CSI NUMA work at the same time. But right now, there's a whole bunch of stuff, if anyone's interested, that we wanted to port to FreeBSD, for example, so Robert Watson is working on that. But also, it's not just a matter of porting it. It's a matter of trying to figure out how do you best use that platform that you've got. So if I'm porting this to FreeBSD, I don't want to just use TCP. I want to figure out what kernel abstractions does it make available, what kind of futex mechanisms, and really just try to win the game of IPC performance as we go through there. And the bigger problem is that we just don't have much hardware, right? It's frustrating to see just the fact that just from looking at the data that we have with just maybe 8 or 9 machines, we've learned so many little facts that we somehow need to encode in our operating system. So Xen and NUMA have significant effects. The architectural variance makes a huge difference, as you might expect, but just how big? What's the implication when you go to AMD Bulldozer versus the Magna cores that we're using right now? Hyperthreads are just this terrible idea that are just stuck around, and when we have our 160-core box, it's a combination of an Intel architecture combined with hyperthreads, and performance just goes all over the place when you're dealing with hyperthreads. Some conditions are just particularly bad. If VM splice, for example, on VirtualBox is terrible. Now, these are all just facts that don't really fit into a framework. How do you use these as a programmer? So what we really want is the ability to run IPC Bench. We want to crowdsource the results. So we're trying to make it as simple as possible for people to run these self-tests, and then just give us kind of long-term data. So if you are Microsoft, for example, then you do get this huge set of interesting performance data from the Windows crash reports, and Google and Valve, for example, gather this for games. We as a community do not do this, and we really do need to start. Because when we're doing this work and designing these transports, I would have loved to have gone back through time to say, well, 10 years ago, what would this have looked like? And there are just obviously a lot of challenges. How do we host this as an open way? So right now we're experimenting with GitHub, so that the idea is you can run IPC Bench with a Python script, and it will just issue a pull request to us. But of course, if we get bored and go into other research projects, anyone can look at these GitHub branches and just do their own analysis and aggregation. But there are some challenges when you actually try to make this real. So how do you version this stuff? So if you're running a benchmark over the course of 10 years or whatever we want to do, someone has to really keep track of this stuff and perform the analyses and so on. So right now, we have a few PhD students who are interested, but overall, I'd love to hear from anyone who can do this. And also, if you go to this URL, you can actually just try to start doing it and just email us the results. We haven't quite finished the GitHub integration so far. So that would be great. So we're also trying something highly experimental that I'm going to spend the last 10 minutes of my talk talking about. And this is super experimental, right? So if you need to flame me, this is probably the time. So I believe that Unix abstractions for communication are just stuck in the dark ages, and it really is time to apply a lot of the lessons we've learned from the last sort of 10 years of especially from network processing, where we have things like OpenFlow and technologies to deal with flows of communication instead of individual packets or individual system calls. So what we really need in Unix is this notion of just making I/O first class. I need to open up a connection to another host, and that connection needs to be persistent. So something is tracking the fact that I am communicating from A to B, kind of a data flow graph. I don't want to have to worry about what the best transport choice for my environment is. I want to just declare the fact that I need a low latency, but I don't mind the occasional pause. I want to declare my constraints and have my operating system or my hypervisor just decide. Also, I'm going to talk about dynamic reconfiguration. So when you're running these communications, why would you want to reconfigure your I/O? So it's actually a really good use. So you're running in the cloud. You've deployed something on Amazon EC2. And what's going to happen? So you're running a web server and a database, and you just configure them, say MySQL. It might figure out it's on the same host, but you tell it to use TCP to communicate, because that's the easiest mechanism. And then when you live migrate to another host, right, under the hood, this might be done automatically by Amazon. It still works, because it's TCP, right? It just goes over the same over the network channel instead. So what happens if you then do some super optimal shared memory transport? So Xen has something called libvchan, which is a memory-to-memory communication. It's really cool. Written by Daniel DeGraff from the NSA, and it's just super fast. It's great. Now, of course, when you live migrate, your database just dies, because it is shared memory, and the memory has just disappeared. And Amazon has no idea what you're doing in your host, in your guest. So it'll just not worry about it. And so what you really want is this atom where something was tracking the fact that there was data going between these. It'll reconfigure it on the basis that, we can no longer use shared memory, therefore I need to switch to SSL, or TCP, and do we even need SSL if it's gone to a remote cloud provider? You want this abstraction where you can just reconfigure stuff as an operating system service and have that just work for you. And so that's where we're working on this system called FABLE. So it's an extension to Unix and to some extent to Xen as well, because it works at many levels. And all we do is we add a name daemon, a cunning name daemon to Unix that gives every process, every entity, a first-class name. So each process might be identified by hierarchically by its PID and by where it is. And you have some flow manager that can keep track of all of the I/O flows between them. So this, for example, is just within a single kind of kernel. Then it might talk to different virtual machines on the host. So these have each virtual machine has its own name. You might then go to a different cluster and have lots and lots of communication flows between them, but they're all systematically tracked either by a cluster-wide name daemon, which we're prototyping using Zookeeper, which deals with fault tolerance and failover and so on, or locally just by a scheduler running in the kernel, or by something running in the hypervisor. You just want to systematically keep track of this stuff. And then the I/O mechanism is natively zero copy. So rather than POSIX, where we bake in assumptions about trust, we're trying to design this low-level API that basically just says, all you have to do is give me a name. You have to connect to a remote host. You have to have the ability to get these buffers that you can read or write into, and then you can commit or release them. So it really is just a very, very simple low-level mechanism, and all of the policy can be implemented in various bits of the kernel and so on. So what does this look like in practice? So if I'm starting up a Fable connection, then I want to establish a handle between my virtual machines. So let's say I have foo and bar, and then this might actually represent a process, or it might represent a VM. I don't really know. And then you connect in a URL type scheme. So I just say, open me up an XIO connection to this other side. Now, because this is a URL scheme, this XIO represents the fact that I want to automatically figure out the transport mechanism. I could also say TCP://:80 to connect to an existing service. This basically just decides, do I want to stay within my Fable world of automatic communication, or do I want to go externally? And so the Fable then takes care of automatically deciding exactly what the communication mechanism is, and it provides a certain amount of future-proofing for your system. So it might decide, well, these two nodes are on the same machine, therefore just go to a shared memory and a few text-based approach because my local benchmarks have decided that's the case, or TCP. Or if you went to the extremely cool talk by Christophe Pasch and our Belgian friends, could it just use multipath TCP? Could it figure out the fact that we can actually have all these different endpoints and we really should be communicating via two routes? Deploying these newer technologies is very difficult right now because we bake in many assumptions about these transports into our applications. So XIO kind of lifts up the game a little bit and tries to make that simpler. So in practice, you can also make things very, very fast with this kind of approach. Because you're separating the connection establishment from your actual buffer management, these individual buffers can be highly optimized for the purpose at hand. So I might have, I want to communicate between these two processes or VMs. I might get a shared memory context that I then get a shared memory buffer that I can write directly into. Or I might get a TCP one where it's page-aligned. It's very, very friendly for the type of network communication you need to do. So if you're trying to do high-performance network communication, you need to ensure that your buffers are page-aligned, because so you can just flip them directly to your target NIC, but also that you reserve some header space for the IP header and the TCP header. Fable just takes care of all that. It just gives you a buffer where the pointer is in the right place, and you just write your data into it. And if you need to write more data, you just request more buffers. So it's a very, very simple mechanism that hides all of the transport details from you at different times. So the uses are myriad for this stuff. So what started off as kind of a fun benchmarking experiment over the weekend turned into a very long weekend, but also the fact that we just found lots and lots of uses. So some of the more concrete things we're putting this for is we can upgrade the ring. Xen is the hypervisor I'm most familiar with, but this really does exist with every hypervisor, is they implement some kind of a user space communication mechanism, and this stuff tends to be very hard to benchmark systematically. So we believe that you can do automatic upgrading of the Xen ring API and dramatically improve, or rather improve the predictability and the performance of I/O. So one of the more concrete ones is that we've been working on an alternative big data mechanism to Hadoop. So how many people know what Hadoop is? Hadoop? Yep, MapReduce, great. Terrible programming model because all you can do is map, reduce. CL is more fun because it's Turing powerful. You can run arbitrary Turing powerful computation on any language. It just uses distributed continuations to let you can write MapReduce in Haskell as just the obvious functions, and CL will take care of suspending and starting up on multiple hosts with fault tolerance and so on. But this is just a great example of, CL is obviously a research project. Hadoop is far more real. But both of these need the ability to communicate and send data across HDFS and whatever file system you're using very, very fast. So just improving the speed of cloud data processing so that you're not scared of virtualization as being slowing down I/O is a big deal. We're also building really fun microkernel systems. So this one is written in OCaml, which probably Richard is the only person who's heard about. But it's an effort to just start building simpler and more predictable guest virtual machines that run directly on the cloud under Xen. So Mirage is a self-hosting system where you write some OCaml code and it compiles directly into a microkernel, which is great until you really start missing Unix, because when you work in microkernels, you don't have all of the nice features of communication selection and stuff that Unix provides you. And so the Fable is actually a support library to deal with communicating between microkernels as well as normal virtual machines. And a lot of this research applies to many languages. So if you want to run Node.js in your JavaScript system as a microkernel, it's actually very straightforward. But this actually gives you a lot of support libraries to just make that a lot more practical in production use. And my good friend Robert Watson, my colleague from the lab, is working on a new project to build reconfigurable FPGA hardware that boots FreeBSD. So this is definitely the most insane project we're working on, but it can also use a bit of future-proofing from this kind of I/O system. So I've given you a bit of a whirlwind tour. I hope I woke you up with some graphs, and I hope you're not going to punch me about my ideas about I/O. But really, what we're trying to do is just trying to understand the complexity of Unix I/O, and we're trying to propose one mechanism to understand it better, which is to build IPC Bench. And I really hope that if you guys have Linux laptops, you can just git clone this, almost no dependencies. I think you might need libnuma-dev, but just stick a pull request or an issue in there and just run that and just give us results. And we promise to make them as open as we possibly can within our constraints, which is, well, public domain, right? And meanwhile, we're hacking on this FABLE system where with the minimal set of intrusions to Linux and to various of the BSDs, we're just trying to transparently upgrade I/O. So there's also an emulation layer in there that works with sockets and so on, and a whole bunch of name daemons. So between these, the goal is next year's FOSDEM, we should be able to do a demo where you have 10 gigabits of throughput between your Xen system, and virtualization should genuinely be an invisible performance hit. So right now, virtualization is beautiful for CPU. It just does not get in the way. But it definitely does get in the way for I/O. And these kind of systems should just fix that problem and just make it really a genuine management gain with no downsides for the purposes of running your high-performance tasks. So with that in mind, are there any questions? Apart from, I need to talk to you about domain NUMA node allocation and such things. Hi. Oh, it's huge. Yeah. So the CL work I mentioned, we actually added MPI support to CL. So I'm actually working with Professor Dave Page from NASA at the moment, and he's got a moon probe called Diviner, and their goal is to ray trace whole planets. And they use MPI to build computation models of the thermal dynamics of the moon and of various planets. And they're hitting this classic kind of scalability curve where once you add more than 10,000 nodes, that's it, you're out of luck. So we're aiming to use this to automatically upgrade MPI-based transports into a more data flow-based model at the same time. So the MPI community has lots of incredibly low-level tweaks to use InfiniBand and transports to make this work. The problem, of course, is how do you move that out of MPI into more general frameworks like Hadoop and so on? So it's actually an active area we're working on at the moment. And I have an unpublished paper on this in CL. I can happily forward you about our MPI adapter for big data at the same time. But yeah, it's definitely a much more general situation. David.
Hi. Do you hear me?
I can hear you. I'll repeat your question.
I'll just speak. Okay, so for this project of gathering data, real-world data, if you're interested at Mozilla, we are working on something on the telemetry, which essentially has the same goal, but for real use of Firefox. So I'm sure we can use the same kind of techniques. So if you want to talk about it, just
that'd be great. That's one of the reasons we don't want to build this infrastructure by ourselves, right? Because we're just too small. So absolutely, I'll definitely have a chat with you about that.
Glad to give a hand.
So to repeat the question, Mozilla is doing a lot of work on open data gathering, and they very kindly offered lots of help to help us integrate IPC Bench with their techniques. And of course, there's a lot more things in IPC that we can measure, right? So you can measure, imagine anything you want to know about your system. Ideally, we want to build a unit test and just gather that data on an ongoing basis. So I think we're running out of time, so I'll happily just hang around and chat to people individually afterwards. But thank you very much for your attention. It's been very, very helpful. Thanks.